If you have AMD, it's named something else, but you definitely do have these instructions in your system. Just gotta look for it. It's a little harder. Right? So the first line we see here, MMX is a single instruction, multiple data instruction set. There's 4 different types of instruction sets. Right? We have this first one, SIMD. We have SI, SD. We have MI, SD, and we have MI, MD. So we know that SIMD is single instruction, multiple data. What does that mean? Any of you guys heard of that before? I think we touched on this like in the beginning of the semester. So, using a single instruction, you can apply it to multiple data, right? Using a single instruction, you can apply it to a single piece of data. Using multiple instructions, you can apply it to a single piece of data, and you can probably guess what that is. Okay. So, let's go into this diagram. Let's see. Yeah. So just so you guys can get a better sense, do you guys see that? Probably not. There we go. So this will be SISD. A single instruction, right, is in the processing unit, and a single data pool or a single piece of data is being handled by that instruction. Single instruction, single data. Let's go with that a bit more. Now we have single instruction, multiple data. We have a single instruction once again, but now it's working on all 4 of these data being outputted from the data pool. Okay, pretty cool. This is a little harder to visualize at first, but here we have multiple instructions working on the same type of data. Notice how this data point is connected to this processing unit and this processing unit. Right? It's the same data, but there's 2 instructions working on it. And lastly, multiple instruction, multiple data. This one is pretty obvious. You have a bunch of data that you're running a single instruction on, and you have another bunch of data, same type of data, you're running another instruction on. Pretty cool. Okay. Now, why is this important to us? Because you guys are going to be learning about how to use that extended instruction set on your computers. Okay? So going back to MMX, let's actually open some code. We'll start at this point. So in that comment area, there's a lot of things you don't see or a lot of things you don't understand, I would say, right? I know that when I see underscores in my code, I tell myself, don't touch it, just leave it alone, I don't want to deal with it, right? Because it looks complicated, it looks hard to read, right? But you guys should be able to figure this out after this class. You guys won't be afraid of underscores anymore, right? The first thing I want to talk about is this data type, underscore, underscore, N128, right? That data type comes from this library, right here. SMMIntrin, okay? This library itself, there's a reason why the ending is intrin. It stands for intrinsic. And primarily intrinsic functions. Does anybody know what the word intrinsic means? I know we only got one guess in the last section. Anybody? Nope. Come on, tell us.
Built in.
Built in. Right. Intrinsic means it's built in. Okay. So we put these 2 things together, built-in functions. Okay. This library has functions that let us use the extended instruction set. Okay? And this isn't the only library. Alright? This is actually one of many. And I'll actually show you how to figure this out. So if you want to find a reference for this extended instruction set and this intrinsic function library, you go on Intel, if you have Intel, and you search up intrinsic guide. Here, you'll actually see a list of a bunch of different functions. Alright, look at that stuff. There's a lot of them. The list goes on and on and on. Alright, it just goes to show you how advanced this instruction set is. Okay, so our instruction set is actually, I believe, using a list of these. We're going to go over, well, at least most of these. Alright, so let's go back to the instruction. We don't know what this type is. How do we figure it out? You know what the library it's coming from is, right? I gave you a reference for it. So what should we do? We need to figure out what this type is. Huh? What? Well, that's one way. You can use it in operation. Or if you don't want to do that, you can go online onto Intel, right? Or on Google. Yeah, search it up. You can do __ M128. Oh, look, there's a Microsoft doc for it. Now, what is this? The M128 data type for use with the streaming SIMD extensions and streaming SIMD extensions to instruction intrinsic. There you go. Doesn't say much, but let's see if we can keep reading and figure out what it means. Variables of type M128 are automatically aligned on 16-byte boundaries. All right. Still, we still don't know what this means. All right. But we can kind of guess. If things are aligned by 16 bytes, what does that mean? Have you guys heard of the alignment in code? Probably not. So I'll give you an example. When you make an integer array, right, and you want to go on to the next element, what do? What's the operation? Kind of like C, let's say C++. How do you go from one element to the next?
You find the multiple of them? Something to do with that?
It has something to do with that. What?
Increment by 1?
You increment by 1. Well, what's being incremented by 1?
The index, correct?
The index. That's right. Now, this is a good starting point for alignment. All right, if you have an array with some index, all right, and you want to go to the next one, you just do index plus plus. Okay. Now there's some more code going on underneath of here. It's not just doing index plus plus and then just it knows where it's going. It knows where it's going. It knows that it's going to the next one because there's an alignment in memory. We know that integers are how many bytes in size? 4 bytes. Therefore, if we do index plus plus and put it into here, we have to go ahead 4 bytes in memory in order to get to the next one. So when your memory is aligned to 4 bytes, it means that every 4 bytes is unique, right? So if I have a pointer here, and for some reason my memory is aligned to 4 bytes, and I decide to increase the pointer in index, it has to jump over to here if I want to get the correct integer. If it doesn't jump to here, I'm going to get half of this maybe, and then the rest of this, whatever that is, and that's going to give me problems. So you use alignment to get that behavior in your memory. Now, if we know that this special data type is aligned to 16 bytes, what does that mean? How many integers do we have in 16 bytes?
4.
4. That's right. So we have something going on for us. We have 4 integers and 16 bytes. Alright, what does that allude to, you guys? If we're saying that we're aligning memory to 16 bytes, what is that like to you? And we have 4 integers in it. It's probably not going to click right away, but what do you do? What's something similar? What do you do? What do you call it when you pack 4 numbers into a certain space? Or what does it resemble?
Encoding.
Huh?
Encoding. Encoding.
No. That's a good guess though. You have a box. You're stuffing 4 integers inside of it. What is this box? In terms of data structure. We mentioned it already. An array. Right, an array. This M128 is really an array. That's all it is. And we're going to see more of it.
Like, what does it do, or why do
Well,
we
we're
need it
going
for?
to get right into it. Watch. Here we see some more M128s. Alright? Notice how for A, it's M128, and we have 4 float point values. So the reason why we have this extension to the instruction set is because we know that pictures aren't perfect. They're not going to be straight integers all the time, or maybe graphics aren't perfect. So we need to use that for float points. Do you guys know how hard it is to do float point computations on a computer? Very hard. They have their own separate module in the CPU. What is it called? I forgot. Float point unit, the FPU, right? It's part of a computer system, specifically designed to do float point arithmetic. Okay. Now, remember, float point arithmetic is very costly when you're doing computation, right? And now let's say you have a matrix full of float point values, and you have another matrix full of float point values, and now you want to multiply them together. Do you see why the 3 for loops accompanied with all that float point value computation is going to take up a lot of time? Not a lot of resources. Do you guys see that? Right? So there's a way to make this simpler. We have this M128 giving us a vector or an array of float point values. Right? We have another one called B, once again giving us a vector and array of float point values. Specifically 4. Do you guys know why there's 4? How many bits is a float point value? Or how many bytes even?
Is it 4?
4 bytes, right? Any float point value is 4 bytes, so how many bits is that?
16?
No,
32.
32. Specifically single precision float point values, 32 bits, right? Now 32 times 4 is 128. Good. This single variable is 128 bits. Yeah. It's 128 bits, but it's holding on to 4 different float point values. Okay? Keep that in mind. I would write this down because he's definitely going to use this in probably one of your tests.
Somewhere write it down.
Alright. So before we progress, now we have a function next to that type. Okay? We have this function. Anybody want to try to guess what that function is? What it does?
Which function?
The one right next to it. So you see you have
The
underscore underscore M128. Right next to that you have underscore MM underscore MUL underscore PS.
Multiply?
Yes, that's correct. How do you know?
It says mol, yeah.
Mol.
It says mol, right? Now what does the PS stand for? Anybody want to try to guess that? You're close. Not quite. It stands for packed single precision values. Okay? Now why is it called packed? Because remember I said that this M128 value is 128 bits in length. Right? So we don't see this as being 4 different numbers. We see this as being one unit.
100. Yeah.
They're packed together. That's why it's packed single precision values. Okay, so as he said, this is a multiplication, which is good. But let's say you want to get into the specifics. We just search it up in this website. So mol PS. And there we go. Now, anybody want to read the description? Let's see if you guys understand it from the description. A volunteer for imaginary bonus points. To be my best friend.
Just to read it?
Yeah, just read it.
Okay. single precision 32-bit floating point elements in A and B and store the results in DST.
Yeah. So it's doing exactly what it says. Multiplying. Multiplying these two hack single precision elements and just spitting it out to DST. And they even give you a little like pseudocode. Yeah. So for j equals to 0 to 3, I, j, 32, yada yada yada, so on and so forth.
Okay, what is DST again?
Destination.
Okay.
Yep. Any other questions before we continue? Yes.
The M128, it says that it's in the Microsoft doc, it says 16 byte,
A line.
a line, 16 bytes, but how can it be 128 is like hacked?
Yeah.
If
So
it's 16 bytes.
So 16 bytes, right? What's 16 bytes converted to bits?
So,
8 times 16. 8 times 16.
8 times 16, right?
that's right.
128,
Alright.
that's why. Okay. Alright, so let's continue. So now let's actually jump into this. Okay, so you guys can all see that. For comparison, we're actually going to be doing dot product. Do you guys remember what dot product is? From linear algebra? Somewhat.
He mentioned it.
He mentioned it. Yeah.
Mentioned, not asked us, though.
He asked you guys? Okay. So just as a refresher,
Someone got it.
a dot product is when you have two vectors, you multiply the individual elements to their respective element, and then you add that all together.
Yeah.
Okay? So, just for a comparison, I'm going to show you the dot product using a for loop, and then the dot product using the special instruction set. Okay? Alright, so let's go to our disassembly window real quick. You guys can see that? Let me scroll over a bit. Alright. So the first thing we're going to look at is this new type that you guys were just introduced to. This M128, right? Notice how there are 4 instructions for this operation. Okay. What's happening here is move SS. What do you do when you don't know what an instruction is?
Google.
Google it. So we go onto Google. We can actually even go onto the intrinsic guide website, and all we have to do is type move SS. Let's go to float or move, either or. See here, they tell you the instruction that it corresponds to, because remember these are built-in functions, and it tells you the description. It says move the lower single precision floating point element from B to the lower element of the ST, and copy the upper 3 elements from A to the upper element of the ST. Alright, that sounds weird. You guys understand any of that? Nope, probably not. And that's okay, because we actually have a debugger to show you guys. So we know that's moving something to somewhere. Alright, it's moving this value, that's here, into this special register that we're going to talk about right now, XMM0. Alright, if you guys do debugging on your computers and use Visual Studios, you will not see these XMM0 registers, because you don't have them enabled by default. So you right click on here, and you click on SSE, MMX, AVX, and it'll show you these these registers. Right?
Okay.
So we're going to progress one instruction. We're going to go forward one. And we're going to see what has changed. What has changed? Yeah, the XMM0, right? What happened precisely? What is that number there? You guys know what that number is? Or at least you know what type it is.
It's a hex.
Huh?
It's a hex.
Not quite. It's float, single precision float. Because these instructions are working on float point values, right? If we convert this into a decimal, what are we going to get back? Let's go into this calculator. it back 1. Okay? Where do we see 1 in our code?
And the first element.
The very first element.
Right, yeah.
So you see we're moving 1 into this register, which was the first instruction. And then what we're going to do next is moving the first thing in this register into the pointer A, or wherever A is. Okay? So we progress, we moved 1 into the stack where A is located.
Okay.
Okay? Any questions? Yes.
So for the first instruction, move SS,
Mhm.
you're moving the actual value of the floating point, not the address to that value, right?
Yes, we're moving the actual value. Yeah. Okay. So this is going to happen for all of these numbers. And if we move forward 1 more, you'll see again that this register has the value at the very end. Once again, there's a reason why it's at the very end. This move SS only takes the lowest bit.
The lowest bit, yeah.
Yeah, it just moves it over into the lowest bit of that register, or the destination. Okay, so let's keep going. Let's load
Wait,
all
so
these in.
it's not gonna move the other values, just the lowest bit?
Yes. So it's going to do it 1 at a time, at least in the instruction right now. In the disassembly code, it's doing it 1 at a time.
Okay. So it's
Right.
moving 1 and then the next, whatever takes its place is moving that, and that's how it's going on?
Not quite. It's moving the value into the register first, right, at the lowest bits,
Okay.
right, and then it's moving it from there, from the register, into wherever A is located in the stack, right?
Okay.
And then when it does it again to the next, to the other numbers, all it's doing is overriding that bottom portion of the register
Okay.
with the next value, and it's moving it out once again. Okay. All right. So once again, we see this happening all over. We're moving B now. We're creating it, and we have floats. Okay. So this is actually interesting, and I just realized this. You see how my compiler optimized this, I guess, this initialization, right? Typically when you make an integer array, let's say, it wouldn't do this. It'll just, I don't know, put it in the stack in a specific order. It wouldn't use these special instructions, right? But here, the compiler was smart enough to say, hey, this is a float array, there's 4 values, let's use these special instructions to load it in faster, more optimized, much better. Alright, so let's skip down. Okay, here's the good stuff. So this is my for loop.
Just looking my chocolate.
Oh, that sucks. So this is my for loop, right? Again, this for loop is computing dot product. Now, I don't know why we have a repetition here.
Yeah, I was asking about that before when I showed you my example.
Let me rerun this debugger.
You're gonna get it. You're gonna double click.
Okay, whatever, we'll work with what we got. So, anyways, but we can see where the for loop starts and where it ends, right? It starts up here, and it ends down here. You can count those instructions. It's a lot more than you need, right? But that's how we do dot product using a for loop and standard float arrays. Inefficient, too many instructions, could be much faster. Now, right under that for loop, we're calling our intrinsic function for dot product. Underscore dot product of pack single precision float variables, right? Or elements. Notice how there's only 3 instructions for this dot product. The move APS, the DPPS, and the move APS once again. Alright, move APS is taking the entire 128-bit, I guess, packed value, and it's moving it over to XMM0. Okay, let's see if we can get a flow going on here. Alright, there we go. So now if I go forward 1 instruction, and we look at our register, Oh, I think I actually skipped over it entirely. Let's rerun. Alright, we're here. So we move forward one instruction. And now we look at our register. You guys see that? So, any of you guys realize something really weird about the way our register looks like? Compare it to the I guess the array itself. So that's A, right? Compare that. Anything weird?
The remaining numbers or something, values?
Not quite. So we know that 3F8 is 1,
Yeah,
right? 404 is actually 3,
3,
and then 408 is 4, and then 3F8 is 1.
yeah. Like it said, it takes the last one first and then 3.
Yeah, it's reversed. Why? Honestly, I still don't know why. But it's a good, for you guys, good research. Some people suggest it's because it's Little Indian. Alright, that's a good guess. Maybe it is. Maybe on Linux, it's completely different. Or maybe on your Raspberry Pi, it's different. Or on a system that's not Little Indian. You know? But it's reversed. So keep that into account.
And the M128, that's the vector that's like floating point, right? Because I remember you gave us like a whole list of that in class.
It's not a vector, right? The abstraction is that it's a vector or an array
Okay.
for you guys to make it easier to understand that. But really, this is a number. In memory, that whole number takes up 128 bits.
Okay.
And the reason why it's called packed single precision elements is because all of those 4 float point values are packed into one number, which is that 128 bits.
Well, we have to know more than 128. Like I'm pretty, because there's quite a few of them.
Yeah, there's like 128, 1256, and
Yeah.
or 256, and so on and so forth. You should know the difference.
Yeah.
Yeah.
Okay.
Alright, so let's go back to our instruction or our function. Alright, so first we move A into that register. Then the next instruction is DPPS. What does that stand for?
School.
What?
School.
Let's Google it? Okay, let's Google it. I like the way you think. It is the dot product. So DPPS. Somebody read that to me and then tell me that yes, this is definitely dot product. Out loud. Out loud.
Conditionally multiplying the packs in precision every bit floating point elements in A and B using the high 4 bits in IMM8.
Mhm.
Sum the 4 products and conditionally store the sum in DST using the low 4 bits of IMM8.
To an average person, does that sound like dot product?
No.
No, right? But it is. We
Why
have
don't
to.
you say dot product?
I know, I don't know why.
Okay.
Right? But it has to do with this thing right here. This IMM8. You guys don't know what that does yet. But we're gonna get into it eventually. Just know that this inline function, or this intrinsic function, I mean, is the dot product function. Alright, and it's tied to this instruction. Okay? So this is dot product. And let's look at the pseudocode. So what it's doing is it's basically taking this IM8 and resolving the stuff that you still don't know yet, right? And it's summing it all together, and then it's probably saving it to a destination somewhere. But let's look back at our disassembly. So we're gonna perform DPPS, right? We're taking B, and we're gonna basically, our destination is XMM0, but that's also where A is located. So we're performing dot product with B and the register XMM0, or 8, right? And you'll see what happens next. We're actually gonna get a bad result because I forgot to change this from last section. So let's rerun this. So continue, all right. Let's go forward. And now we're gonna do the dot product. And now let's look at our register. So anything weird? What's the dimension of dot product after being performed on a vector? As in, how many numbers do you get back?
One.
One
One, right? It's a single dimension thing.
single dimension.
Yeah, but here we're getting all of them. We're getting that single number in all 4 locations in this register, right? This has to do with the IMMA value, okay? Just know that this is what the dot product value is. And you guys can do it if you like. I'll actually calculate this for you. It's supposed to be 10.
Okay.
Alright, let's look at our functions or our
I have a quick question.
yeah,
What is that 0B111 when you multiply dot product?
we're gonna get to that. Yeah. So if we do the dot product for these 2 vectors, 1 times 1 is 1, 3 times 1 is 3, plus 1 is 4, 4 times 1 is 4, plus 4 is 8, and 1 times 2 is 2, plus 8 is 10. Crazy. And all it took was 3 instructions compared to our
Magic.
Yeah, magic. Alright, the last instruction here is moving this register into C. And C just happens to be one of these packed numbers. And that's it. Dot product. Now, let's talk about what that IMM8 value is. So according to the website, we're going to use the high 4 bits to decide which numbers we want to multiply. So, let's see what that means. So, our current IMM8 is in hex FF. Right? Haven't lost you guys yet? FF and hex. We saw a bunch of 1s. It's 8 bits. FF. And let's say we have A as 1, 2, 3, 4, and B as 1, 2, 3, 4. Since our IMM8 is FF, we want to look at the high 4 bits and determine which one of these do we actually want to multiply in our dot product. So we have F's, right? That means we have 1, 2, 3, 4 for that first F. So the high 4 bits are telling us we want to multiply this one with this one, this one with this one, that one with this one, this one with this one. So we're multiplying all of them together, right? If I were to change this to 1110, what's gonna happen?
Only the first 3, right?
Let's go with that. The first 3, right? But notice how it's only doing 3 of them. Okay?
Okay.
Okay, good. And if I just had all zeros here, what then?
No.
None of them?
None of them.
Okay.
Nothing happens. Right? Now,
Why'd you
this,
go,
what's up?
Why'd you go,
Don't worry about it. So this remaining 4 bits, the lowest part, according to this, it says, and conditionally store the sum in DST using the low 4 bits of IMH. So these 4 bits are actually going to tell us where we want to store the sum. So if we want to store it in the first index of the destination, we'll have this. Right? If we want to store it in the second index, we'll have, if we want to store it in the first and the second, we'll have this, and so on and so forth. Okay? So is that clear to you guys what this IMM8 does?
I have a quick question. So
Yes.
if the value is, the result of the dot product is 1 value, why do we need like 4 bits for that?
See, that's the thing. Maybe, I don't know, you want to, instead of keeping it at a single dimension, you want a whole vector that's just a repeated value of it, right? To do more math afterwards. That's one reason.
That was the reason the value was printed 4 times.
Yeah, because we had FF as our IMM8, right? Okay, good. Now, going back to what you were talking about, there's a reason why I said, and you'll see it now. So, like as I was saying, we're gonna do the example where I just have that last bit in the upper region, 0. Right? According to Evan, he said that we should only do the first, second, and the third index. Okay? Okay. So now let's try it.
No.
Alright, so we're here. Right? We're right here. We're gonna go forward one. We're gonna go forward again. And look at our register. What value is this? Let's see. That's 9. Evan, according to these vectors
It
here,
should have been 8, yeah.
Was
Can-
5. Oh.
is 1 times 1 plus 3 times 1 plus 4 times 1 equal to 9?
No.
No, right? So what's really happening?
Is it going the reverse order or something?
It's going the reverse order. It's doing the last 3 elements. Why is that? Something we hit at like close to the halfway point of this, I guess. Something about the registers, right?
It's in reverse.
It's in reverse. So when you have 1, 1, 1, 1 as your upper 4 bits, you're taking all of them. When you have 1, 1, 1, 0, you're only taking these 3 values.
What if we have something on like 1, 0, 1, 1, or we just ignoring the second?
Yeah,
Okay, cool.
that's right.
And if that's the case, 1, 0, 1, 1, what second value would it ignore?
The third.
From the start or from the end?
It would ignore the 4.
The 4.
Okay.
Right? Yes.
Why would the value of I m and 8 not be FF? Or why wouldn't you want to multiply all 4 elements to be right?
That's a good question. And I wish I was a graphic type of guy to be able to tell you, or somebody who used these vector instructions very frequently.
But essentially, like what we just did, that we got the value of 10, it was 1, 1, 1, 1.
Mhm.
Multiplied all the elements, right?
Yeah. I mean, I'm pretty sure there is definitely some functionality to that. Maybe somewhere in the field of mathematics where you might want to ignore one of those index user elements. Alright. So we learned what IMM8 is. That's great. Now you're probably telling yourself, how do I just use the assembly instructions instead? If I don't want to use these functions, why can't I just write assembly for it? Well, lucky you guys, you can. Let's move on to this section. So if you're using Visual Studios and you have Intel and you're on Windows, you can do inline assembly in this format.
Yeah.
Double underscore ASM curly brace. You can write the assembly code you want. Right? If you want to use these instructions, you have to first understand that you have to set your memory, or at least you have to set the memory of the variables to be aligned to 16. Since we're not using the intrinsic functions, and we're actually declaring it ourselves for this assembly instruction, we have to make sure we align it. And you use this to align it to 16 bytes. Okay. Now notice how after that, it's the same thing. We have M128, and we just have these arrays or vectors or packed elements, right? And we move on to our assembly. So the best part about this is that since you can write inline assembly, you can decide what registers to use. If you don't like the registers that the compiler uses, maybe you don't want to use one register and then multiply that register and just store it in the same register. You know, you can decide that on your own using the assembly. So let's run this. Let's continue. Continue again, one more time. So we are now in the assembly region. Notice how the instructions are exactly the same into this assembly window. Okay? And once again, if you don't know what any of these instructions are, or if you don't know the instruction that you're trying to use, you go onto the intrinsic guide right here. You search up the inline or the intrinsic function you want to use. Let's say I want to do absolute for some reason, and they actually give me the instruction. Okay? Alright. So what is this doing? Oh, it's doing dot product once again. Okay, but this time, instead of having an IMM8 value of FF, we have F1, which is doing what? What?
Right. You have in the register just one value instead of all of them.
That's right.
The
And-
last byte.
Bingo. Yep. Let's see if that's correct. And where are we? Right here. Let's see, I haven't moved forward yet. There we go. Right there. Last byte. Good. Alright. So we see dot product. That's boring. We're done with dot product. There's a whole bunch of other functions that you guys will probably have to learn. And we're just going to go over probably another 2 more. So the first one is multiplication, which we already spoke about. You're multiplying A times B in vector form. Okay? And again, it only takes 3 instructions, which is great. The next instruction is a little trickier. Right, the name doesn't really give it any justice. It's MMHadd. Yes. Anybody want to tell me what that is? Or want to try to guess? Huh? Hex addition? No, but good guess. One more for 1,000 points.
What do we get after this 1,000?
I don't know, man. I guess appreciation. Alright, so I don't think any of you guys will get it unless you were at my first section. But it's this thing called horizontal addition. Alright, anybody want to try to guess what horizontal addition is like?
Oh, yeah, just right now.
That's not horizontal.
I'm sorry.
You would think it's just straight across, but not quite. Right. So we have, again, 2 of these half numbers. 1, 2, 3, 4. 6, 7, 8. If we do a horizontal addition, this is what it means. Take these 2 numbers, add them, and save them into, let's say, C0. Right. Take these 2 numbers, add them and save them into C1. Take these 2, add them into C2, and take these 2 and add them into C. So you see how you're only adding the 2 pairs next to each other. Alright? Let's go on the website and see the reference for it. So underscore HAdd, yes. Horizontally add adjacent pairs of single precision floating point elements in A and B and pack the results in DST. Alright, and here's the little pseudocode bit for you guys. So you see, it's magic. Why would we need that? I don't know. But once again, it's there for a reason. So it made somebody's life easier. Maybe not yours, but somebody's. So let's progress. Let's see. So let's multiply. We're multiplying A times B. Alright? And we're moving that to X, M0. And then we're saving that result into R1. Alright? Now we're also taking R1 and doing horizontal addition with R1. And we're saving it to R2. So first off, what's A times B? Wait. Not 10. Remember, we're
Oh, right, we're doing that.
it's a vector multiplication. So what is it? What's the result of A times B? 1, 3, 4, and 2. Right. So remember that 1, 3, 4, and 2. The next instruction that we have is here. We're going to take that result 1, 3, 4, and 2, and horizontally add it to itself. What's the result after that?
It's gonna be
2.
4, and then 6 twice.
Yes.
4,
4, 6, 4, 6.
Yeah, 4, 6.
Now let's move forward to see that happening.
Wait, if you add it to itself, like, what do you mean? Like, if there's A and B. Like, do you add it to both A and add it both to B?
No. So if you're so if we're doing horizontal addition, all right, and let's say it was A and B in this case, we'll do it this way. Okay, we add A and A, A and A, B and B, B and B, right? If you're doing it to itself, you would have, let's say, 2 A's, right? But the same thing would apply. You'll have 1 plus 2 and 3 plus 4, and then you'll have 1 plus 2 and 3 plus 4, all over again. Okay?
I see. Okay.
Yeah, okay. Cool. Alright, so what's the result? As he said, it was what?
4, 6, 4, 6.
4, 6, 4, 6. So let's move forward and let's see it for ourselves. And there we go. So now let's see if this is correct. This should be what, according to Evan? Sure. Should be 6.
6. It should be,
And it is
should be
6. And the other one should be 4.
4, yeah.
And we know it's 4 because we've seen it before. Cool, right? Again, I don't know whose life this made easier, but it did somebody's life, you know. And then we're doing it again. You don't have to give me the answer for that, don't worry. And this last thing, the store SS, it's just moving things. That's it. And those are intrinsic functions. Any questions?
No.
So, yes.
This is like a little bit earlier, but IN and A, the second value, so that the first value determines which elements of the array are multiplied. The second one is where there's like how they're stored. So if it's 1, 1, 1, 1, where that mean that it'd be
It'd be stored in every section of the register or the destination,
okay.
Yeah.
The XMI register.
or whatever the destination is given. Yeah. All right.
Can we
Any
go
other
back to the
questions?
arrays?
Yeah. So, which one? These?
The one that we just recently did, the 4, 6, 4, 6.
Okay. All right.
Does anybody have a hard drive?
Anybody guys have?
No?
Yeah, I need those.
Do you have a question, Connie? Now, how do we get 4, 6, 4, 6? So first, remember we did A times B, right? And we saved that into something. I'll go to the instructions so you can see it. So right here. Okay. First we did A times B, and we saved it into R1. Then we did horizontal add R1 with R1, and that should have gotten you the 4, 6, 4, 6. Do you see it? You can go through it again. So A times B, the result of A times B would be 1, 3, 4, 2. Alright? And if we horizontally add 1, 3, 4, 2 to itself, we get 1 plus 3, which is 4, and 4 plus 2, which is 6. And we do it again, 1 plus 3, which is 4, 4, and 2, which is 6. Okay. Any other questions?
What kind of questions we can expect on the test?
No idea. But let's.
On which test?
There's a lot more to this. The latest.
Can we do something crazy like just like go, you know,
Well, let me
dive
tell
into
you.
the deep end and just like see how if you can swim?
Let me tell you though.
Lewis,
There's
a
a lot
face you
more to
made.
this. Right.
Yeah.
So with AVX, right? AVX is another version of, or at least more instructions really, right? AVX added a whole bunch of things to this. It added more registers. It added more instructions. It added a bigger data type, right? Because you need bigger data types if you want more registers with bigger registers. So let's actually look at those registers.
Monday. In class.
Look at these amazing things. Oh, I can't see them from there. So
Oh dear God.
right here, you see those